So hi guys, so today we would be starting up with another part of ML theory, that is hyperparameter tuning and model selection. I would just start with a small example. Now suppose this is your model. So this is your model, and now you are evaluating your model, and you are evaluating a simple model, just enough, just use a test case. Now suppose you are hesitating between two models. There were two models here. These are the models, yeah. And say this one is a linear model and this is a polynomial model. I would just mark P, yeah. And how can you decide which one to take for your main production? So one option is to train both and compare how they will generalize using the test set. Now suppose after you did that, the linear model performs better, but you want to apply some regularization to avoid overfitting. The question is, how do you choose the value of regularization hyperparameter? One option is to train 100 different models using 100 different values for this hyperparameter. Suppose you find the best hyperparameter here, and that value produces a model with the lowest generalization error. Means suppose you have got this and it's giving you the lowest generalization error. So once you have got that, you will launch this model into production, but unfortunately it does not perform as well as you were expecting it to perform on your testing data or training data. What just happened? The problem here is you measured the generalization error multiple times on the test set, and you adopted the model and hyperparameters to produce the best model for that particular set. Now what can you do after this part? Means you are stuck in a situation where you have already done the model on testing set, but even after that it is not performing well. This means that the model is unlikely to perform as well as bad on the new data also. Hence, a common solution for that is using a cross validation. And there is another thing that is called holdout validation. So we would first talk about holdout strategy. So it works like that. You would split your data into training set, and I would just first show you a figure from my side. Suppose this is the training set. This is the training set. Now you would first split this model into two parts, that is training. This is training, means and this is validation. You split your training set into training and validation set. Now suppose you have got three model here, that is model 1, this is model 2, this is model 3. I would just use another pen for clear things. This is 1, this is 2, and this is 3. Now what you would do, first of all you would train it here. All the three models would train on this data. All the three models are being trained here. Now what would happen after training? You would validate them on this data. You would validate them. Now after this you would expect the results. Now you would see that this is providing you 25% results accuracy. Now this is providing you 55% accuracy, and this is providing you directly 87% accuracy. So obviously you would choose the third model. So this is how we are going to doing. The problem that is that you measured the generalization error multiple times on the testing set, and you adopted the model and hyperparameters to produce the best model for that particular set. This means the model is unlikely to perform as well as on the new data. Hence you splitted the training data into two data, that is test training and validation, and we will choose the best model out of these three and train the whole model. Now we would choose this third model. We would just choose directly this third model and train it on this this whole training data. Since the final model will be trained on a much smaller training data, it would be like selecting the fastest sprinter to participate in a marathon to overcome this. Hence, there is another thing known as cross validation. But we would be covering that in the next video, because I want that holdout validation part should be understood in a very significant way. So what we did, we split the data into two parts, training and testing. For each parameter combination, we trained a model, and we computed the metric on validation set, that how did the model perform, just like we did here. We saw that model third performed better on this, and after that we choose the parameter combination with the best metric, and we would retain that model on the training data and compute metric on test data. So what is the advantage? You already tested it on the validation part, which gives you advantage over other models which have been directly trained on their training data, and now they are being tested on the tested data. So this is the part where you are performing the holdout validation. That training set has been split into training and validation. Now, to overcome this problem, there is also a problem of known as the sprinter problem. That this is just like you are participating in a race, and the fastest sprinter to participate in the marathon wins. Suppose you can imagine like this. This was the race, and this is the line. Now, suppose the first model reach here first, the second model reach after that, and the third model reach after that. Now, the first one who reached first would obviously win the race. It's obvious, and the second one reaching would obviously lose the race. So to overcome this problem, we come up with a technique known as cross validation, which we would be covering in another video. Then another video would be consisting of two parts, that is cross validation and data mismatch, to cover the whole topic of hyperparameter tuning and model selection. So thank you for watching the video. Thank you and have a nice day.